So the equations that we encounter won't always be of this nature. Sometimes they'll be more complicated. But again, the important thing is that we know we have options in terms of solving them. Okay? So first going to run through the guess and check method. And again, when I think about the guess and check method, I think of what powers of 4 I know. Okay? For example, I know 4 to the first is 4. Okay? I know 4 squared is, help me out, 16. And I might not know, but my calculator does, that 4 to the third is 64. Okay? So if I'm looking at these two numbers, 16 and 64, 50 is between there somewhere, kind of more toward this side than this side. But I know then that my exponent has to be between 2 and 3. Okay? Again, I know that when I try, guess and check, I'm going to try 4 to the 2 point something. Okay? And again, because it's closer to 64 than 16, I might go 0.5, I might go 0.6, whatever. All right. Let's try to determine this using this process of trial and error. Let's try to determine this to the nearest hundredth place. Okay. Again, I'm going to try 4 to the 2.5 first, and then figure out, what is my tens place, and then what is my hundredths place. All right. See if you can figure that out by guess and check or trial and error. And so I discovered 2.5 wasn't big enough, so I just kept going, okay? And now I'm between 2.8 and 2.9, all right? Now, sometimes you get one answer that's too small and one answer that's too big, but you still want to pick the closest one, all right? So now I'm going to be trying 4 to the 2.81. Okay, can probably do better than that. You guys know about second enter, right? Okay. And so I try, oh, that's good, 4 to the 2.82, okay? How far is that away about? 0.14, somewhere around there, all right, 0.13. And if I try that, this is 0.56 away. So I do want to pick the one that's closest. Here's what I'm saying, 50 minus 49.8, I'm going to round that to 7. All right, that's 0.13 away, but 50 minus 50.56, that's 0.56 away. So which one would be the better answer? 2.82. All right. Okay, so one option. Again, they're not always that easy, so sometimes guess and check can be long, cumbersome, difficult. All right, wasn't so bad there. Next strategy, there's a lot of side conversations going on that shouldn't be. Next strategy is by graphing. Okay, you guys should know that your calculator is a wonderful tool. You paid a lot for it, so you should know how to use it. All right, whether it's in physics or in math or whatever. So good solving technique, type this in y sub 1, this in y sub 2, find out where they cross. Okay, so do that with me, please. In y sub 1, type in 4 to the x. Y sub 2, type in 50. Now, this is not going to look great on a standard window because 50, our window normally goes up to 10. 50 would be way up here. So we have to think about that, all right? So x's are fine on a standard window. I'm going to use negative 10 to 10. Bigger than I need, but that will work. And then again, I'm interested in where y is 50, so I just made my x minimum 0, but you could leave it negative 10. And x max, I always like to make it a little bigger than the maximum because otherwise you get a line right across here and it's hard to manipulate. Okay. So a window, something like that. Some of you have luck with zoom out. I don't generally have luck with zoom out. And then we graph it. Okay. And we want to find this spot. All right. How do we find that spot? Intersect. All right. And we just get close to it and then we hit enter. Whoops, not that. We get close to it and then we hit enter, enter, enter. And sure enough, that just confirms our 2.82 answer is a good one. Okay, 2.822 if we wanted to be even a little closer. Now again, some of our equations, and if you want to show your work, or if your teacher, me, wants you to show your work, some of these other strategies will be useful as well. Okay, here is the strategy of using log or natural log. One of the big reasons that logs are useful is when you want to find an exponent that's a variable, the log allows you to bring that down. And this is how it allows you to do that. If you take the log, I'm going to use common log, but it really wouldn't matter which one. Common log of both sides. Remember that the rule still applies. What you do to one equation, you got to do, or one side of the equation, you got to do the other side. Okay. But again, all those rules we were talking about here, okay, this exponent then can jump down in front because of that log to a power rule. And then we'd have x times the log of 4 equals the log of 50. And then what would be my last step to get x all by itself? Divide by log of 4. Okay. And these cancel. And again, I know you know what the answer is, but it's good to make sure we're typing these in correctly because our calculator will give us a parenthesis that we need to close. And so there's that same answer again. Okay. And the last one, in case we're not sure our answer is right yet, okay, using the definition of log and the change base theorem, I'm going to kind of divide my paper here because I want you to kind of see that these work out very similar. Again, if I write the problem down, 4 to the x equals 50, okay. The first part of the strategy says use the definition of log. Well, that's this. If b to the y equals x, which is kind of what we have an exponential one, then the log base b of x equals y. Now, I've told you before that I always find this rule harder to go this way than this way, okay, because here it's just like a circle, you know, and for some reason unwrapping the circle I think is harder. All right, but if we take a look at this compared to this, what would our equation be calling the letter b? 4. What would our equation be calling the letter x? 50. And this is interesting, but what would our equation be calling the letter y? X. All right, they're not always going to match up. So when I unwind it and write it as a log, it would be log base, help me out, what goes in place of b? 4. Of, help me out, what goes in place of x? 50. Equals, what goes in place of y? X. All right, again, as weird as that seems. And do you remember the change base theorem that allows us to type non-base 10 logs into our calculator? Again, what that says is that the log of 50 divided by the log of 4, and now you see, oh, wow, that's what we just did over there, okay, would give us x. Again, we'd want to remember to close our parentheses, but we'd still get 2.82, etc. Okay? So again, although sometimes options are frustrating because you're like, oh, I don't know which one to use, you know, they're actually valuable because if you forget this one, you know this one, or vice versa, or you did this one, you want to check it with that one kind of thing. Okay? All right, second example, more words. I wouldn't write all these words even if I were taking notes on this. I'll give you some shorthand stuff to write in a minute. But please take a moment to read through this example. Should be quiet. So often this formula is referred to as the PERT formula. It just kind of looks like it says that, all right? It also is on your sheet, okay? The variables are defined here. Interest rate is a decimal. T is the time in years, okay? P is the initial value. In this case, that would be the initial population. So as you read through here, what was the population initially? 250 million. Let's see, and it's growing at a rate of 1%, which is what as a decimal? 0.01. Common mistake is for people to make 1% 0.1. That's not 1%, that's 10%, and that would be growing a lot faster. Okay, but it's common. We just move it, and we always think it goes in front of the number or whatever. Okay, and then the only other thing we know is we know that the final population we're looking for is 300 million. So now if we plug that into our formula, okay, we have 300 million equals 250 million times E, which remember is a number like pi, 2.718. It's just we use E to represent it, to the R as a decimal, 0.01 T. Once again, we're trying to find T. When is the population? So we're trying to find T. And in order to do that, we got to use this equation. But before we can bring the T out front or anything like that, we got to get rid of this 250 million. So let's divide by 250 million on both sides. Okay. Over here they cancel. Over here the millions cancel. Okay. So 300 divided by 250 is 1.2 equals E to the 0.01 T. Now, one of the things I referred to on our last problem over here is when you want to find a variable that's an exponent, take the log of both sides, and then you can bring that down in front. Similarly here, except when you see an E, use the natural log instead of the common log. I'll show you why, all right, in just a minute. So take the natural log of both sides. Got to get everything out in front of the E first, but then you can take the natural log of both sides. Then bring this down in front. So we got the natural log of 1.2 equals 0.01 T, natural log of E. Now here is the only advantage over using natural log versus common log. Okay? Will you type into your calculator, please, the natural log of E and tell me what that is? What is the natural log of E? It's 1. Some of you are going, I don't know where my natural log button is. All right, natural log is right here under common log, so you can go natural log. And then you can do second natural log. That gives you an E, but then you have to do the first power, okay? And I don't think it cares if we close parentheses. Or you could do natural log on your divide sign. Second divide is a regular old E without a exponent thing, all right? So the natural log of E is 1. So that's where the payoff is. We get to just cross that out and forget it. Okay? And then divide by 0.01. Again, if that was common log, we'd have to divide by the common log of E and then divide by 0.01. Not a big deal, but it does save you one step. Okay? Do that division, again, remembering to close the parentheses. Be ready to tell me what or how many years this will take.